Hello, welcome to the final video in this section. In this video, I'll be discussing some consequences of and further examples using Green's theorem. So first, before I get started, let me remind you what Green's theorem says. So in the last video, I introduced Green's theorem, and it provides this relationship, which is shown on the slide, between line integrals around the boundary of a region R and double integral over the region R. And so we have two possible examples of regions shown at the top of the slide, the yellow regions, and in each case, the boundary of the region is traversed anti-clockwise, and that curve going around the boundary in the anti-clockwise direction is called L. And when we have this set up, we know that the line integral of a differential form p dx plus q dy around the boundary of the region R is equal to the double integral of qx minus py. And these are the partial derivatives dq dx and dp dy. So I covered this in the last video, and today we're going to look at some consequences of this, some applications of it really, and then some further examples using Green's theorem. So the first consequence I'll discuss is that if qs x equals py, that's the partial derivative of q with respect to x, equals the partial derivative of p with respect to y, then this qx minus py equals 0, which means that the line integral of this differential form p dx plus q dy around any closed curve L is equal to 0. It actually doesn't matter what L is, because when we have a closed curve, then this line integral will be equal to the double integral of 0 over the region enclosed by the curve, and the double integral of 0 will be 0. So, well, here's the explanation I just gave. So, by Green's theorem, this line integral will be equal to this double integral over the region R of 0. So let's do a quick example of this. Find the integral of this differential form y dx plus x dy around a circle. And so we have a line integral around a circle of y dx plus x dy. And you remember p is the coefficient of dx and q is the coefficient of dy in the differential form. And we have then that py, the derivative of p with respect to y, is equal to 1. And qx, the derivative of q with respect to x, is also equal to 1. And so, by Green's theorem, this is equal to the double integral over the region enclosed by the curve C, a circle in this case, or the region enclosed would be the disk, of 1 minus 1 dA. And so this is equal to double integral of 0, which is 0. And in fact, the example says, what is the integral of this differential form around a circle? But in fact, the same would be true. This would be equal to 0 around any closed curve. It's a very general statement, so very far-reaching. And so this has applications in physics. Differential forms that satisfy this correspond with so-called conservative vector fields, where there's a potential, and this figures into the theory of motion in physics. I'm not going to go through the details of that, but this is an application of this concept that comes from Green's theorem. Okay, so that's one consequence of Green's theorem. A second consequence is that we can use line integrals in order to calculate areas. So we have a region R which is enclosed by a closed curve L, and the area of R is equal to the line integral around the boundary of R of the differential form x dy. So this follows from Green's theorem, because in this case we have that p equals 0. Remember, p is the coefficient of dx, and q equals x, and so qx minus py equals 1. So this line integral is equal to the double integral over R of 1, which is just equal to the area of R. It would be the volume of the cuboid, or maybe not cuboid if R isn't a rectangle, but the volume of a block with height 1 above the region R, which is equal to the area of R. And one thing to point out here is that there are also other differential forms that have the same property. So here we have the line integral of this differential form x dy. But in fact, there could be other choices of p and q so that qx minus py equals 1. There's infinitely many other choices. And they would all give the area when we do the line integral around the boundary of a region. So this is also quite general, really. For example, we could also take p equal negative y and q equals 0. And then py is negative 1, qx is 0, and so qx minus py is 1 again. So if we did the integral around L of negative y dx, that would also give the area. And there are many other choices as well. Now let me do an example of this second consequence, calculating the area of this region, which is shown here, which is enclosed by the curves y equals x squared and y squared equals x. So I'm going to calculate actually this area in two ways. You may have seen problems similar to this in calculus in the past. You can calculate the area between two curves like this by subtracting two single integrals. So first let me draw the curves and the area we're trying to calculate. So the bottom curve here is y equals x squared, parabola. And the top curve here is x equal y squared, which is a parabola opening up to the right. And the region that we want to calculate is the area in between these two curves. And so we can calculate this area by taking the single integral of x to the 1/2, which gives the area above the x-axis and below this top curve, and then subtracting the integral of x squared. And that gives us the area in between. So let's calculate this area in that way, and then we'll also calculate it by doing a line integral according to Green's theorem. So we'll calculate the area using two methods. So first, just using single integrals. And so the area of this region, as I was saying, is going to be the integral from 0 to 1 of the top curve, which is x to the 1/2 equals y, or y equals x to the 1/2 square root of x. Take the square root. The area underneath the top curve and above the x-axis would be integral from 0 to 1 of x to the 1/2 dx, and then subtract the area underneath the lower curve, which is the integral from 0 to 1 of x squared dx. Will be this area we want to calculate. All right, and so these are simple integrals. We can do this in a fairly straightforward way. So this will be 2/3 x to the 3/2, the indefinite integral of x to the 1/2, minus x cubed over 3, evaluated from 0 to 1. And so we only get something non-zero when we plug in the limit x equals 0, and this becomes 2/3 minus 1/3, or 1/3. So interestingly, this area is 1/3 of the area of the unit square, which is 1. So this is actually dividing up the unit square into thirds. It's a bit surprising, I think. All right, and then let's also calculate this by doing a line integral using Green's theorem. All right, so remember that the area, according to the previous slide, of R is going to be equal to the integral around the boundary of R, so that boundary traversed in the anti-clockwise direction, L of x dy. And so we need to do this line integral, and that will give us the area. Now let's look back up at the region. So the boundary of this region, traversed in the anti-clockwise direction, is L, and we want to split it up into two sections. One section going along the bottom part of the boundary and the other section going along the top part. Be L1 and L2. And we'll compute the line integrals over each of those separately. On L1, y equals x squared, and x goes from 0 to 1. And then on L2, x equals y squared, and y goes from 1 to 0. So this is going to equal the line integral over L1 of x dy plus a line integral over L2 of x dy. So we'll calculate those two line integrals separately. And on L1, this was the bottom curve where y equals x squared, and we will use x as the parameter, y equals x squared, and we're integrating x dy, so we need to know what dy is. dy equals 2x dx, and x goes from 0 to 1 on that part of the curve. So the integral, line integral over L1 of x dy is equal to the integral from 0 to 1 when we use x as the parameter of x dy. So x and then dy is 2x dx. All right, so this is the integral from 0 to 1 of 2x squared dx. The indefinite integral is 2/3 x cubed. Evaluate from 0 to 1, which gives us 2/3. And this is the integral of x dy along L1. Now let's do the line integral along L2. Now on L2, well, on L2 it is easiest to parameterize using y as the parameter, and because the formula for L2 is x equal y squared, you could also use x as the parameter, but let's use y. So x equals y squared, and well, what we want to integrate is x dy, so we don't need to calculate dx, although you could, of course. Dx equals 2y dy. And y on L2 goes from 1 to 0 because of the orientation of the curve. Y is in the interval from 0 to 1, but the curve goes from the top to the bottom because we traverse the boundary of the region in the anti-clockwise direction. And so in the integral, y goes from 1 to 0. The integral over L1 x dy is the integral from 1 to 0 of x, which is y squared, dy, when we use y as the parameter. So this becomes y cubed over 3, evaluated from 1 to 0. So we plug in 0, we get 0, and then we plug in 1, and we get negative 1/3. And so this line integral is 2/3, the L1 part, and then minus 1/3 is the L2 part. So the area is, again, 2/3 minus 1/3, or 1/3, which is the same we got from the other method. You might think that doing the single integrals is easier. It does sort of involve less computation in this case, but this provides a link between these two things, which is pretty non-obvious, and so is something that could have applications, a different way of calculating the area. Okay, those are the two consequences of Green's theorem I was going to discuss, and I would like to do one more example of Green's theorem, which is not actually related to either of these two consequences, but is just another example using Green's theorem. So we're going to calculate a double integral both by directly doing the double integral and applying Green's theorem. And this is a double integral over a circle or a disk. And so we want to calculate the double integral over d, where d is the disk of radius 2 of x squared dA. All right, and so d is this disk centered at the origin of radius 2. And we're going to calculate this both by doing the double integral directly and also by using Green's theorem to convert it to a line integral around the boundary. So this is d, the disk, and we are eventually going to use the boundary in the anti-clockwise direction, which will be L. So let's first just calculate this double integral directly. And this is labeled as A in the question. A. Calculate double integral directly. And here we're integrating over a disk, and so we'll use polar coordinates. So the things we need to know in order to apply polar coordinates for this integral are just what x is, because y doesn't appear in the integrand. And remember, x in polar coordinates is r cosine theta. Y would be r sine theta, but we don't need to know y in this case. And we need to know what the area form dA is. dA is r dr d theta. All right, and so this double integral, when we write it in polar coordinates, is r squared cosine squared theta r dr d theta. So this is x squared, and this part is dA. Okay, and so to calculate this, we convert it to an iterated integral. We also need to know the limits of integration when we want to integrate over this disk of radius 2. So let's first write the double integral without the limits. So combine the r squared and the r, which becomes r cubed, and then cosine squared theta r. The inner integral will be with respect to r theta. Now, the disk is radius 2, so r on this disk goes from 0, center, out to 2. So the limit for r, the limits for the r integral will be 0 and 2. And this is, again, a disk, just like in the examples we did previously when I discussed polar coordinates. So the limits for theta just go from 0 to 2 pi, go all the way around the disk. Okay. So now these are one-dimensional integrals, and we can do them. So we first need to do the integral with respect to r. We find the indefinite integral of r cubed. That's r to the 4th divided by 4. Cosine squared theta remains the same, and r goes from 0 to 2. Okay, and so we evaluate at r equal 2. Then we get 2 to the 4th is 16 divided by 4 is 4. So integral from 0 to 2 pi of 4 cosine squared theta d theta. And we have to remember how to find the indefinite integral of cosine squared, or look it up somewhere. And remember, in order to find the indefinite integral of cosine squared, we use a trigonometric identity for cosine squared, that cosine squared is equal to 1 plus cosine of 2 theta divided by 2. When we use that trigonometric identity, we get this is integral from 0 to 2 pi of 2 times 1 plus cosine of 2 theta d theta. And then we can write down the indefinite integral of that, because we can recognize the indefinite integrals of each of the terms. So we have 2 theta plus sine of 2 theta for the indefinite integral. And when we evaluate sine of 2 theta at either 0 or 2 pi, we get 0. And so this term just contributes 0. And then this term contributes 4 pi. So this double integral is 4 pi. All right, that is directly computing the double integral. Now let's compute it by converting it to a line integral and then computing that line integral. So let's start again from the top. This is the situation, the diagram of D. And so what we want is to use Green's theorem. Let me remind you what Green's theorem is, what it says. And so we want this double integral of x squared dA to be equal to the double integral of qx minus py. So what we want is to convert this to a line integral where x squared equals the qx minus py. This is similar to when we were finding the area in the second consequence of Green's theorem, where we were just doing the double integral of 1, and we found a q and p so that qx minus py is equal to 1. And here we have x squared, and so we want to find q and p so that qx minus py is equal to x squared. And again, like in the other case, there are a number of possibilities, and infinitely many possibilities, in fact, for q and p that you could choose that satisfy the equation qx minus py equals x squared. The easiest way to find such q and p is to simply assume one of them is 0. So let's say assume qx is equal to 0, or assume q is equal to 0. And then we just want py, negative py equal x squared. So let's say if q equals 0, then what we need is that we need py equals negative x squared. And so when we can find the indefinite integral of x squared with respect to y, we just get p equals negative x squared y. And you could even add a constant here, but that would just make the integral we have to do more complicated. So you may as well just say p equal negative x squared times y. But once again, there's many possible choices for p and q that would also work in order to calculate this double integral using Green's theorem. So by Green's theorem, this double integral over d of x squared dA is equal to the line integral around the boundary of d in the anti-clockwise direction of p dx plus q dy, but q is 0. So negative x squared y dx. And so we'll calculate this line integral, the line integral around the boundary of the disk of radius 2 of negative x squared y dx, and that will give us the double integral. So in order to do this, we need to parameterize L. And the easiest thing to do is to parameterize L by the angle theta. And this is the angle theta. Theta will go from 0 to 2 pi as we go around the disk once. So if we parameterize by the angle, we get that x equals 2 cosine theta, y equals 2 sine theta, as we go around this circle of radius 2. And well, here in the line integral we want to calculate, we have dx. We can calculate dy as well, of course, but we don't need it. Dx will be negative 2 sine of theta d theta, and let's just calculate dy. dy would be 2 cosine theta d theta. Okay, and so that theta goes from 0 to 2 pi as we go around the circle, and so we have all the information we need in order to expand this line integral as an integral of, well, as a single integral. So this line integral L negative x squared y dx is equal to the integral from 0 to 2 pi, the limits for theta, of negative x squared, that's negative 4 cosine squared theta, x squared, times y, 2 sine theta, times dx, which is negative 2 sine theta d theta. All right. So we have then integral from 0 to 2 pi. There are two negative signs, which will cancel out. We have 4 times 2 times 2, so that's 16. And then cosine squared times sine squared. All right, and as in the previous case, we get an integral that involves powers of sine and cosine. This one is actually more complicated than the previous one, a bit more difficult to find the antiderivative. But once again, you do it using trigonometric identities. And so when you have cosine times sine, you can recognize that that's a trigonometric identity for sine of 2 theta. Sine of 2 theta equals 2 cosine theta times sine theta. So if you use that double angle identity for sine, you get that this is the integral from 0 to 2 pi of 4 sine of 2 theta squared d theta. And then you have to use the trig identity again in order to simplify this sine squared of 2 theta. And the identity you use is that sine squared of 2 theta equals 1 minus cosine of 4 theta divided by 2. It's another version of the double angle identity for cosine. And so you get the integral from 0 to 2 pi of 2 times 1 minus cosine of 4 theta d theta. And from this we can recognize the antiderivative. And so we would get 2 theta minus 1/2 sine of 4 theta d theta. Oops, sorry, not d theta. Evaluate from 0 to 2 pi. All right, and sine of 4 pi evaluated at either of these endpoints, 0 or 2 pi, is 0. So as similar to the previous case, that term contributes 0, and we just get 4 pi, which was what we got when we calculated the double integral directly. And so Green's theorem works once again. We get the same result when we calculate using this line integral. Okay, this is the end, or the last video about double integrals, line integrals, and Green's theorem. In the next section of the course, we're going to move on to discussing numerical methods.